Okay. Good morning. Some of you are probably up late last night. Sorry I took out the internet apparently all across Butte County, at least so I'm told in Canvas Inbox. So apologies that my project deadlines caused the internet to go out. It may have been the case, which I'm sure was stressful. Okay, anyway, so I know we just got finished with the project. I'm going to try to make the stream efficient today. Um, because probably people are tired, and so we are having a normal work week, but I'll try to make the stream um, not go 2 hours and not even go an hour and a half. But anyway, kind of short and efficient, and get you what you need to get the lab, um, and then we'll move on. So the projects take me a long time to grade. One of the downsides to the style of parsing in a file of commands and then having you do specified output is that it can be very challenging to hunt down bugs that way. So I could have just unit tested it, but I also wanted you to walk away with the experience of doing that, of having an input file, having your output match a specification so that you have that in your background. But anyway, that's going to make it take me longer to grade, just so you know. I'll do my best. I got up super early this morning and I've managed to do a couple. So anyway, I'll get them out there as soon as I can. And then I will also I will create an announcement and put a link to the input file that I am using to evaluate your submissions. Okay, so let's get into it so we can be efficient today. So yeah, I will. I too get to pay a price for that style of project, but I hope that the experience will serve you well. Hi, good morning, Magenta. Good morning, Edcast. Happy Monday, everybody. So, I hate to say it like this, but we're starting the last project cycle, and we've only got 3 weeks to do it. So our labs, even way more so than last time, our labs for the next 3 weeks are directly addressing what the fourth project requires. So these few remaining labs are very, very important if you want to make your life as easy as possible for the last project. Anyway, I know you're tired. So in the act of doing the lab this week, you will be preparing part of your solution for the last project. But as soon as you feel recovered enough, you should start on the fourth project because the turnaround is a little bit quicker than normal. Yeah. So someone in chat's just saying that they did want to get that experience, but it has been has made for the end of the project cycle to be more interesting than it might otherwise be. Okay, so we're starting a new data structure. And I'm going to be, as I said, efficient as possible in describing it to you, talking about the initial algorithms for dealing with it. And sort of two challenges. It's a dynamically linked structure, so you will be creating nodes and linking them. But it works different than a linked list because we're building trees, and specifically what's called a binary search tree. So the nature of this data structure is to be sorted, and one of the ways that you can kind of master the concept of the data structure is to build them by hand. So I mean, like, just list out some pretend inputs. I'm going to do it here in just a moment, and build a tree by hand so that you have a picture of how conceptually your structure should look when it's populated with data. So yeah, we'll do that. The other challenge about the binary search tree is that it uses recursive algorithms heavily. If you didn't use recursive algorithms on a binary search tree, it would be way more miserable. So it is very much worth your effort to try to get as comfortable as a person can get in a month and a half of their life with recursive algorithms. You're going to get practice here. You're going to get more practice at some point down the road. The upside to Project 4 is that we have the same kind of reading commands from an input file and mapping those in in a decision tree onto a data structure. So that part of the setup is going to be very, very familiar to you. Yeah, so unfortunately, I don't have any notes about Project 3 yet. That'll have to wait till next week. So let me switch over in the interest of being... actually, let's walk through the module. So we're going to create a new structure called a binary search tree. It's going to have some similarities. It's going to be built of nodes. It's going to use a sentinel. So remember, the doubly linked list had a head and a tail to mark the ends of a doubly linked list. A binary search tree has a root node, which is the only sentinel that uses is marking the sort of the first member of the tree, and then all of its descendants come after. We will look at how to insert nodes into binary trees. We will look at how to what's called traversing the binary tree, which is to visit all of its nodes in the interest for us of printing its contents. And then we'll look at an algorithm to free all the nodes. So yeah, there's a fair amount going on. And the function interface is going to be slightly different. Of course, because it's a different data structure, but also because we're going to do a slightly different setup so that we'll have sort of a public set of functions on our binary search tree and then a private set of functions on our binary search tree. And I'll explain to you why we're doing that. So a bunch of readings on binary search trees. A lab, which, by the way, they rebooted Replit this morning, and I believe it's back. Okay, it's back. That may help some of the latency issues that people were experiencing. So I've already got a REPL set up for the lab so we can work through it together. I'll have you do a little bit more exploration of some additional issues about C++. C++ has just become such a vast language with so many features. I actually would criticize the C++ language for this. C++ never saw an idea in programming that it didn't like, so every idea that everybody uses in programming finds its way somehow into the C++ language. You can argue that's a good thing. Because it means you can do sort of all of the different techniques that people are doing. And if there's a new technique, it will quickly find its way into the language. The downside is that it makes for a very complicated language with a lot of things that one needs to kind of study over time and keep up with. So Magenta's asking in chat about the tree form. So I'll come back to your question, Magenta, about how the tree is built and make sure that I've answered it. So first, I'm going to just get through the module, and then I'm going to go draw some pictures. And I think I'll answer, but I'll make a point, Magenta, to answer the question. So, and for those of you watching, there's a question I'm going to let linger for a moment until I start drawing pictures, and then I can answer it better. And I'll read it as well. Okay, so reminders this week. Lab as always, discussion as always. I'm going to do the complete labs implementation on the live stream. Inside of this hour that I hope to get done in. So you will see all of what is needed, and I'm going to run the lab myself to make sure that I'm passing all the tests so that if you watch the live stream and implement as I have implemented, then you'll be good on the lab. And then maybe you can take a little bit of time to get your breather that you need from the last project, start thinking about the final project and then maybe drawing some pictures for yourself to develop an understanding of a binary search tree. So individual project 4, that's the next and last project that's due the end of week 16. So during week 17, we will do one more data structure together, but it won't find its way into a project. It will just be one last new content so that you exit the class with as much knowledge as I can deliver to you in 17 weeks. All right, let me switch over and draw pictures. Hopefully this is going to work. Yeah, okay. So a binary search tree is built on nodes, and the nodes look like this, at least conceptually, right? So there is content, and then instead of next and previous, we say left and right. Technically, this is the left child and the right child. Left child, right child. So it's kind of like a family tree, but upside down from how we will sometimes draw it. Although on Ancestry.com, they draw it this direction. So nodes look like this. They have content. They have 2 links to other nodes. One to a conceptual left child, the other to a conceptual right child. That is the binary search tree node. And then the binary search tree itself is this. Is a sentinel to keep track of the root node of a binary search tree. And of course, the binary search tree is all of the algorithms that allow us to insert, remove, locate nodes. I will tell you up front that by far the hardest thing to do on a binary search tree is remove a node. It is very difficult to remove a node from a binary search tree. So what we will do is we will use that opportunity to read an algorithm presented in a textbook and translate a sort of a technical algorithm into code just from the words. And that's another experience we'll have with this binary search tree. So binary search tree node. The binary search tree itself is just a sentinel marking the what's called the root node, and then the algorithms that allow nodes to come in, nodes to be removed, nodes to be located, that kind of stuff. Traversals, which is the way we iterate over all of the nodes in a binary search tree. So let's build one so we can see how this looks. So I'm going to just distinguish between a binary tree and a binary search tree. So a binary tree, the important thing about it is that it is unsorted. We're not going to do a binary tree, but if you hear the term binary tree, it's just a thing that looks like this. And there's data inside all the nodes. Some nodes are kind of at the dead end. But anyway, the difference between a binary tree, which is unsorted, and a binary search tree, this is the one that we are doing, is that it is sorted. So when we construct in code a binary search tree, that's the one we're doing, we expect that all of the nodes will be sorted. And this is going to look weird at first, although it's going to sound simple. So in a binary search tree, everything to the left is less than. So if I go to a node, everything to the left of that node is less than what's in the node itself. Everything to the right is greater than. So that's relatively simple to understand. What makes a binary search tree is that the data is sorted, and the way it is sorted is that if you go to any node in the tree, everything to the left, it will be less than the data in that node, and the data, everything to the right of that node, will have data that's greater than the data in that node. That's relatively easy to understand, that part. But let's build one. And this is the activity that I recommend if you get the lab knocked out and you still have a little bit of energy. You should read the 4th project and maybe think about firing up a REPL for it. But this is another thing you want to do in preparation for the lab and project 4 is just take some numbers. It doesn't really matter. just write down some numbers and then build a binary search tree of them. So if I had these numbers and I were inserting them in the order that I received them, left to right, this is how it would look. The 16, because I have no root node for the tree yet, well, the 16 just automatically becomes the root node. So that's relatively easy to understand. So I've inserted the 16. Now the 27. So the 27 is going to be inserted by following a binary search tree's rules. And because we only have this one starting place, we always start at root to find the spot where a new piece of data should go. So if I start at root with my 27 and I see what's in root, well, it's 16. Well, 27 is bigger than 16, so I have to go to the right. And the moment where I find an empty spot, which I do right here, I'm going to attach a node to hold the new data. So there's the 27. All right, the 99. So how does that work? Well, I start at root. 99 is greater than 16. So I go to the right, and I see that 99 is greater than 27. So I go to the right, and then I find I'm at a dead end. So I put the 99 in. Done. The 42. So the 42 is bigger than the 16, so I go to the right. The 42 is bigger than the 27, so I go to the right. The 42 is smaller than the 99, so I go to the left. I hope I left room to build this tree. There's the 42 done. The 15. Well, if I start at root, 15 is less than 16. I'm immediately at a dead end. So I can attach the 15 right there in that spot. 77. Bigger than root, bigger than 27, less than 99, bigger than 42. So this is an exercise I highly recommend. Even maybe write yourself a little random number generator and just let the computer spit out a list of numbers and then start building a tree. 33, start at root, bigger than 16, bigger than 27, less than 99, less than 42. '88, bigger than 16, bigger than 27, less than 99, bigger than 42, bigger than 77. It's a very cool data structure. One thing you'll notice, by the way, and this is if you go on to a place like Chico State, what comes after what we finish with in this class, we finish with this kind of thing. What comes next is how do I make these things balance themselves out so that I have roughly the same amount on both sides everywhere. We will not be balancing things out. We will just let them land as they land, which could mean that we have a very sort of unbalanced kind of right-heavy tree. That's fine. Okay, so there's that. I'll give you another couple of terms, even though we don't really need them in this class. So a node that has no children, no left child, no right child, that's called a leaf of a tree, which makes sense, right? It's the thing at the end of a branch. So 15 is a leaf. Where are the other leaves? 33 is a leaf. 88 is a leaf. So that's one term. Another term that we don't really need a lot, but just so you've heard it, is depth. So depth is basically how deep is the deepest node from the root. So there's one deep from the root. There's 2, 3, 4, 5. So 88 is at level 5, starting kind of at 0 and counting up. So the depth of 88 is 5, which means that the deepest point of this tree is 5 depth. those are just terms. We don't need them as concepts for our algorithms, but so that you've heard them. Um, we do talk sometimes in terms of the leaves on a tree and the depth of a tree. Um, we would rather not, we don't have the algorithms for it in our class, but we would like to have a less deep tree, which would suggest that it's more balanced on the left and the right halves. But we don't worry about balancing. So anyway, this is an important exercise to go through. Write or generate or use a website or whatever to get a set of random numbers, and then populate a tree by going through that process. Start at root, left or right. The next step, left or right. The next step, left or right, until you find a spot where a node could be placed and then attach it. These things are hard to draw because you want to do nice, pretty kind of spread out branch links, but you start to run out of space unless you have like a big old wall or something to write on. Okay, so there is building a binary search tree. Last concept before we look at some code. So we're going to be doing algorithms that are recursive, and a recursive algorithm on a tree. I will tell you the way that I worked it out in my head, but this may not be the way that you work it out in your head, but it does take some thought and some drawing pictures, and then kind of looking at code and what does it mean to work it out. So a recursive algorithm on a tree treats every node as if it were the root of its own little subtree. So what we call the root of the tree is the whole thing. But if we were to recurse to the left of root, we would find ourselves kind of with a window on 15, which thinks of itself as its own little subtree. And if we were to go to the left from 15, we would get to another subtree. So anyway, these recursive algorithms kind of start at the root, and then they start moving to smaller windows of subtrees. So if we go right from the root, we end up at this subtree. And if we go right from 27, we end up at this subtree. If we go left from 99, we end up at this subtree. If we go right from 42, we end up with this subtree. If we go right from 77, we get this subtree. And then if we go right or left from this, let's say left, we end up with a subtree that's waiting for a new root to be planted, as it were. The hardest thing, in my opinion at least, is getting comfortable with the sort of image in your head of subtrees. So as soon as we go left from root, start at root, as soon as we go left at root, we're only thinking anymore about this being the tree that we are working on, right? There's the 27 subtree, the 99 subtree, the 42 subtree, the 33 subtree. And our algorithms will actually kind of descend into these subtrees looking for an empty spot, typically. Okay, so what does all that stuff look like in code? Yeah, okay, I can deal with the other stuff as we go. So let me get... So anyway, I'm not posting the complete code, but I'm about to write it. So I'm going to implement this entire lab for your viewing. Okay, so the first thing I'm going to do is I'm going to what's called stubbing, S-T-U-B. I'm going to stub functions because I think if I try to compile it right now, I'm going to get errors. Yeah, so you see the seg fault down here means that something is bad. So I'm going to stub the functions. And what I mean by that is I'm going to go to the functions that have return values, and I'm going to put a return statement that satisfies that return value even if it's not correct. And what I'm trying to do is getting into a compiling and running without crashing state if possible. So that one, this one returns something. So I'm going to go ahead and just quickly get it into a not crashing state. We have some functions in the private section this time, so I'm going to respect those. Print in order. Okay. So let me see if I can get it to run without crashing. Well, that's all I can do because I've stubbed out all the functions that can be stubbed out. So we'll just start implementing some stuff. So all I did, when I say stub, S-T-U-B, all I did was I found the functions that have return values, and I put a return statement that would satisfy them, even though I suspect that's not correct for every case because I have written no code. So that's called stubbing, and sometimes stubbing your functions with return values will get you past the compiler. Yeah, so I don't need so the question Magenta is asking is, what about this unsigned int here? It's just an integer variable, so there's nothing I can stub about it. So that one is what it is. I'm looking for the functions when I stub specifically that return things, and just putting something in there to satisfy them for the compiler. Okay, so hopefully Magenta, I forgot to refer back to Magenta's question. So the tree would take several sublinks to a main link hub, and then each of those sublinks would have sublinks. So hopefully that matches what Magenta. So Magenta had already sort of pictured what I was about to draw, which is you imagine this root node and then sublinks, sublinks, sublinks to build the big tree and its subtrees going all the way down. So hopefully the pictures did actually answer that. All right, so it'll compile, but the unit test crash. So I'm just going to start writing code until I find where the fix to the crash is. And I'm going to go for the easy stuff first. So the binary search tree. Okay, thank you. So Magenta is confirming that was what they wrote in words in chat. It was actually correct, and then did end up matching what I drew. Okay, so let's start with a constructor. And let's look for the data members. So we'll go down to the private section. In the constructor, what should we be doing? Is it initialize the tree with size 0 and null root? So let's find those variables that we need to initialize. Okay, so in the private section, we have a size, should make that be 0. And we have this struct. The struct is using a different setup, which I'm going to tell you about in just a second. But it's defining a struct for a binary search tree, so it contains data and it contains links to link up left children and right children, or left subtrees and right subtrees if you like to think that way. And then it has a constructor that takes data and then stores the data and nulls out everybody, although the constructor is using a new style, and I'm going to explain that to you in just a moment. But anyway, pointer to root is the other data member, size, pointer to root, and then some functions in the private section. Okay, so size, pointer to root. So you are seeing something new in the node down here, which is the way this constructor has been written. Notice that there's actually no body to the function. There's this list of the data left child and left child data members with values in parentheses next to them. So for a constructor, you can, and this is handy in other contexts, but I just want you to have seen the idea. Instead of actually doing the data initialization in the block, you can do the data initialization in what's called an initialization list. For us, we are just going to see this as a syntax option, but it turns out that these are very useful should you ever find yourself in a situation where you are using inheritance, which we're not going to do in this class. But this initialization list, if you've seen it at least once, then when you see it again, you will understand what it is, which is a different way of initializing the data members of an object. So I'm going to go fix our binary search tree constructor to use, instead of a block, an initialization list. So it would look like this. We do a colon. Sometimes you will see people do an initialization list on the next line down. It's totally up to you. So right after the constructor name, you can initialize, and the way you initialize in this list is you put the data members by name and the initial values that you want. And when you do that, you no longer need the block because you've already done the initializations actually prior to executing the block. For us, this is just going to look like a different way of doing it, but there are some cases where inheritance is being used in C++ where this initialization list can come in a lot. It's very, very useful. For me, I like to do it this way when I am able to do so because I think it looks nice. So when I see a constructor and I see a colon after it, I know I'm looking at an initialization list. So data member, initial value. Data member, initial value. If we look at the node, it's doing the exact same thing. In this case, the data field is using the parameter as its initial value, but then the left child is using null pointer as an initial value, right child, null pointer as an initial value. Okay, so that is a new thing that I wanted you to see in the scope of this class. Now we have it for using an initialization list to construct our binary search tree instances. BS tree says clear the tree, which is probably a reference to clear. All right, so I'm going to go ahead and call that. I'm going to go ahead and hit it with the compiler as I go. So right now, all I've implemented is the constructor and the destructor for the binary search tree. The constructor using an initialization list for the two data members, and the destructor, which is simply going to call its own clear function to delete the nodes. All right, so I'm just going to see if I get any further. Still crashes. I can live with that for now. I already know what to do with get size to fix it, which is this size. Clearing, I'm going to put that off until we've got some inserts done. That will do the clearing for us. So now here's another new concept. We have two insert functions in here. In the public section, just reminding you where we're at, the public section, we have this insert function. So this function is the function that will be called should our binary search tree library be used by someone in their own application. They would simply use their instance of a binary search tree dot insert some data. Oh, notice, by the way, it's a template, but probably you saw that on my way by. It's a template. So all in one header template. All right. Where were we? Oh, insert. So there's a public insert, and then there is a private insert that's a little bit different because it has not only the data, but also a pointer to something called troot. So we're going to implement our binary search tree to try to secure the sentinel from the outside world. And what I mean by that is if some other program where we're using my binary search tree, I don't want them possibly screwing up the root pointer and screwing up in doing so my whole tree. So I'm going to keep all of the node pointers hidden from the outside world, the other programmers in the mix, by simply exposing to them a form of the function that doesn't even make reference to the root node. So hopefully this makes sense the more times I repeat it, but just know that in this library, our binary search tree data structure, we're going to have public functions that are simplified and that hide any mention to the outside world, because the outside world really only sees bool insert data. Internally, we will deal with all of the pointer stuff. So we're trying to keep it as simple for other programmers as we can by making them just think tree insert data Whereas we know, well, actually, we're going to have to do something with pointers internally. All right, so what does this look like? We have to return something. So you're going to notice that the public form of insert returns bool and the private form of insert returns bool. So the public version is simply going to return the result of calling the private version, and the private version is going to insert starting at the root. So in the code that I write, the pointers are present, but in the external function calls, the pointers are hidden, which is a security measure, so some third-party programmer doesn't do something bad with my root pointer. But it also makes the other programmers have to think less about the dirty details of my tree. They just say insert data, but what I know actually happens is, well, actually, I'm going to have to like work my way down in the tree to find my spot. Okay, so I'm going to, instead of returning true or false, I'm actually just going to call the insert and return the result of my internal work. All right, so what does that look like? Starting at root, just like I did when I was inserting by drawing a picture, we're just going to left, right, left, right, left, right until we find a spot. All right, I don't want to get hung up on this too much today because I think probably everyone's fatigued. But you'll notice this ampersand here. So I'm going to tell you what it is this time, and I will come back and start this discussion over about what this ampersand on a pointer means. So let me switch over to the picture, give you a quick view of what that means, but not have you worry about it tons. So the difference between a node star and root versus a node star root in a function. So this ampersand, you may or may not remember, but what it means is a reference to the original. So what does it mean when we talk about pointers that are copies of pointers versus references to the original pointer? So in the case of root, the original root is this. It's the actual sentinel in the tree. A copy of root would be me taking another pointer and pointing it to the same place where root goes. All right, so that's not that big a deal. Let's do a harder one though, and I wish I left myself more room here. Yeah, let me just do it down here. So let's do this instead. Do a harder one, and then we'll go implement some code. Okay, so now we're going to look at the difference between a reference to root left left pointer versus a not reference or copy of root left left pointer. So here's root. If we go to root and then we go to left and we go to left, we get here. But what this means is, I'll get rid of this leaf thing. So if I say reference to root left left, I mean root left. I mean this thing that's actually inside the tree. This is very important because when we are adding nodes inside of the tree, we need the pointers to be the ones that are actually the links in the tree. Yeah, so I'll address that, Magenta. You're exactly right in chat. So the ampersand gives us the link that is actually internal to the tree. So what Magenta has said in chat is the copy pointer is like a temp pointing to whatever that location is. And the problem is, and that's true. So here is the copy, points to the same location, but if we hang a node here on a copy, we're not hanging a node inside of the internal structure of the tree and the thing don't work. So when you see these, just know that the algorithm is intending to alter the internal structure of the tree itself and not just access information. Okay, so that's probably enough without digging too hard on that. All right, so we are in our private insert. We are doing things to the internal structure of the tree, which is another reason why we made this function private. It's in the private section, because we don't want third-party programmers messing up the internal structure of our tree. Okay, so here's the funsy part, which is going to look just like super obvious, but try deleting this and writing it for yourself a few times. It's not as easy as it looks. So what does it mean to insert some data in a root? Well, it means to find a spot. All right, so how do we find a spot? Well, the main thing we're looking for is that this isn't really temporary, but what I mean to suggest here is that it's a link that is at some point in the structure of the tree, but not necessarily the actual root. It could be the root, but it might not be the root. It might be another link that we've descended down to in the structure of the tree. But what we're looking for is for this parameter being null. Which is kind of weird sounding at first. It seems backwards and counterintuitive, but the whole point of the algorithm is to find this spot where we have a link in the structure of the tree where we can attach a node. And I'm actually going to use the link in the structure of the tree to generate my new node. So I'm actually allocating the node dynamically, and I'm literally connecting it right into the actual structure of the tree because of that ampersand. So this is a new node that has been connected right in to the actual structure of the tree. We should increase the size of the tree. That's the whole point of the algorithm. Now, the other thing to notice here, well, you'll notice it here in a second, so watch what happens next. So what if we're not looking at an empty spot? Well, if we're not looking at an empty spot, then we're looking to see if we should go left or go right. So if the data is less than the data that this node has in it, then we're going to use recursion and actually just reset the entire process one step down. So, oops, I forgot to return true here because we got one in there. But if instead we're looking at a node that's already occupied, a spot that's already occupied, then we need to figure out if we should go left or right. So if we need to go left, then we actually have to wait to return the result of going to the left. So let's try that data to the left. And that's it. Now this is recursion because I'm calling the same function, but setting it to start at a subtree, the left subtree. So the reason why we did this first is because this is the break case. So we found the break case first, which is the point where the algorithm can dead end, it can stop and finish. This is not a break case. It has to go back in, but to the left and try again. We also have the possibility that the data needs to go to the right. If that's the case, then we're going to use recursion to take that data, but send it down into the right subtree. We're being careful to return the result of that descent because we have to wait for that descent to complete to know if we succeeded or not. There is one other possibility here. So we are going to create a binary search tree that will not allow duplicates because that is more complication than we want to fight with. So we have actually 4 possibilities when we try to insert data in a tree. We found a spot and can insert a new node to hold that data on that link in the tree. Or we need to descend into the left subtree because we found an occupied spot and we have data that should go to the left. Or we found an occupied node and that data should go to the right. This else part means that the values match. The data, it's not an empty spot. it's an occupied node, and our data is not less than it, it's not greater than it, it is exactly the same data. And in that case, we're not going to allow it. So we're going to return false and just say you're not allowed to put duplicate data in. That is the whole insert algorithm. It is recursive, and it actually has two breaking cases. When we find an empty link in the tree, we can make a new node there, or we recurse to the left, or we recurse to descend to the right, or we found a node that has data that matches, which we will not allow, and we will return false, which is a no, I'm not doing it. Let's hit compiler. Okay, we're still crashing, but the tests do attempt to run. In fact, I don't know if you guys saw this. It's possible that we need to manually delete things. I put this in the early on discussion last week, so one of your classmates was having this issue, and hopefully those of you who needed this saw it. Because we are doing this all-in-one header file, it's possible the compiler won't pick up the changes. So we will remove the executable, we'll remove this intermediate compiled file, and then we'll run again and see if we get a different result. Yes, we did. In fact, it doesn't crash anymore. That's good. It might not have been crashing that whole time a long way back. I'm still failing tests, although I'm passing 15 and 19 now, so we're looking pretty good. Okay. So I'll go do one last at the very end. Let's implement another so we can get out of here. So clearing. There's a public clear. Notice that there's no reference to ND pointers, and there is also a private clear that is going to be altering the internal structure of the tree because it needs to pop those nodes out of there. So it doesn't have a return type. We don't have that to worry about. But if some third party calls our clean, neat, you can't see the pointers public version of the clear function, what we know we actually have to do is fire up a clearing algorithm in the private form of our function that is going to get into the details of the pointers. So this is for all the other programmers in the world who might use my tree. They just say tree clear and don't worry about it. But I know that I actually do have to worry about it. All right, so let's go do the private one. We are going to be, here it is, altering things in the structure of the tree. Makes sense. Okay, so this one's kind of funny, but we do have, we don't want to be trying to delete anything if we're looking at a dead end on the tree. So we're only interested in nodes that are actually there. And then this part is tricky because you have, I'm just going to quickly switch over and draw a picture of what I'm about to do. So if you just had a simple tree like this, let's say, and if we had T-root sitting right here, well, we also got to clean up the children. We need to make sure these get deleted. And if we delete this node before clearing off the children, then we're going to crash the program. So we actually have to wait to clear this parent node until we have cleared off the two child nodes. So here's what that looks like in code. All right, so only nodes that exist, and then we are going to clear the left, clear the right. We could clear the right first and the left first. It doesn't really matter which of the two children we clear off first. We just need to clear off the children before we clear off the parent. So we will delete the parent node last and then make sure that we null it out. That's it. That's the whole algorithm. The break case is just sort of a else part that doesn't do anything. So I'm not even going to put it there. But if we get to a dead end, then there's nothing to do. So, but we don't even need code to represent that. If it's a dead end, nothing happens. That's fine. Okay, and then next week we'll start by reviewing a removal, a clearing process to see how it would work. But let's go ahead and clear that. Do I still have the remove in there? I don't. So I'm going to list it. So I don't see a main.o, but I do see a main. So I'm going to remove that, and then I'm going to run it again and see if we manage to pass any more than the 15 of the 19. Still only passing 15 of the 19, which means that this print thing is the last problem. Notice that the print has the same kind of clean public form of it that doesn't expose any of the pointers, and then we have the kind of unpleasant private form of it that does have to deal in the pointers. Notice, by the way, that we're not using a pointer reference this time because we don't need to alter the structure of the tree. We just need to access the data inside of it for printing purposes. I need to look and see what the output expects. It looks like it expects new lines. All right, so that's what I'm going to try. All right, so print in order. So you'll notice, by the way, that the public versions of these functions, they pretty much always just fire off their private partner with the root pointer. So Magenta asks, when clearing, what if the left child? So I'll do one Magenta as my closing thoughts if I have time. I'll show you a clear. This handles it because the recursion actually automatically descends into the tree. So if I have time, Magenta's asking, what about the children of the children? The recursion will do it, but I'll do a quick example so we can quickly see how that works before I close out. Okay, so let me get the print in order and then we'll finish on that note. So anyway, the public form of print in order does not expose any of the gory details of the root, but it does call the private gory details version of the print in order. So a print in order, and I'll switch over quickly and show you. A print in order means that the 5 should print, then the 10 should print, then the 15 should print. So left child, myself, right child. That's a print in order. And that's actually all you have to know to get the algorithm, but feeling comfortable that that's happening is another problem entirely. All right, so here's the print in order. We're going to do the if troot not equal to null, because we don't want to try to print null stuff. Troot not equal to null. Then we print the left child. So we print in order the left. We print ourselves, which it looks like I'm supposed to put a new line there, and then we print the right. And then I'll show you, I'll have a few minutes to kind of draw a picture of both clearing and printing so you can make sense of it. But I recommend that you kind of, I'm glad Magenta asked about how are these actually working. Like what about the children of the children? So this is a good thing since I've given you all the code to practice on. So let me, let's do the same routine. So clear, I'm going to see that there is a main, I'll remove it. And then I'll run. That's just a guarantee that the compiler is going to reset. I have the wrong size somewhere. Oh, goodness gracious. Every time I delete one on clear, I need to reduce the size by 1. Forgot about that. And then I'll draw a quick picture, and then I'll also kind of put the code on the screen for you. Oh, you're right. Okay, so Magenta has had a very good insight to share, which is Recursion is kind of like a while loop that descends until it can't descend anymore, and that's a fair way to think of it. The recursion causes repetition to happen that kind of descends down into the left or descends down into the right. Sometimes kind of switches back and forth. It's super super cool. It's just impossible to see in code, but you're exactly right, Magenta. The reason why these recursive algorithms cover the whole tree is because they are repeating themselves down into the structure of the tree until they hit null pointer dead ends. Pretty cool stuff. Okay, so we are passing. So I'm going to do two things in the couple minutes that I'm going to, before I give you a shorter day of it. So one thing is to draw a picture real quick of, and I bumped my camera. Okay, so let me just draw up a quick tree and we'll look at printing first. And then we'll look at deleting second. So we'll just put a 20 out here. So here's the tree. So print in order, what that does is it starts by printing on root. But what root does is it says, if my location that I'm at, which would be here to start, is not null, then I'm going to go to the left first. And then the function resets itself recursively. So this is still waiting for this area to finish. So it goes left by recursion. So now we have a recursive call that says I'm going to need to work on this tree. Okay, so this tree, which is now kind of the root of its own tree, says as long as there's a node here, there is, then I'm going to go to the left first. Fair enough. Now we're on this tree. Recursion. So we've recursed down. We're 3 layers into recursion. This node says, well, I'm going to go to the left first. Goes to the left, and then the algorithm says, if this is not null, do something. If it's null, do nothing. So nothing happens. Print myself. Then go to the right. Nothing happens. So this little subtree is done. Now we're back to this one who had gone to the left. Now he's going to print himself before going to the right. This one, before it tries to print itself, goes to the left. Nothing. Prints itself. Goes to the right. Nothing. Now we're back up here. Prints itself. And then goes to the right. This one goes to the left first. There's nothing. Prints itself. Goes to the right. So now we're on this one. Goes to the left. Nothing. Prints itself. Go to the right. Nothing. And that's the end. It's all done. Pretty cool though. See how it came back out in order, even though it wasn't necessarily a guarantee that it would. Okay, so how does the deleting work? So if we start the clearing, we'd start here, and this thing would try to clear its left first, and then its right before clearing itself. So start here, we'd say, well, I got to clear the left. Well, and this one says, well, I got to clear my left and my right before I can clear myself. So we go here. This one says, well, my left and my right have to go. So it goes here, but there's nothing there. Goes here, there's nothing there, and now it can clear itself. Now that this one has let its left subtree clear itself, it's going to let its right subtree clear itself by recursion. So we come down here, clear the left, there's nothing, clear the right, nothing, clear myself, clear myself. Now this one has said, well, my left subtree has now cleared itself. Now I'm going to wait for my right subtree to clear itself. So we get here, tries to clear the left, nothing, tries to clear the right, which tries to clear its left, its right before clearing itself. And now that its right has cleared itself, it can clear itself. And now that its right and left have finished, it can clear itself, and the whole tree has got popped off. So it's pretty cool. And if you want to put some debugging outputs in here and write yourself a little application, the unit test won't expose this, but if you make yourself a separate application with the tree and put some outputs here and there, it can be helpful to kind of see what order things are happening in. I agree, Magenta. It's a very, very cool thing. It is so awesome and so easy once you get it. And it takes such a long time to get it. because it's easy to look at the code and say, yeah, that makes sense. Um, but one thing that I recommend that you guys do is, I mean, take the code that I've given to make sure you're passing the unit test. But if you have time, you might like just fire up a separate one and see if how close you can get to implementing these recursive algorithms on your own. So I'm going to go back up and I'm just going to review the code that I wrote so it's on the screen. So all the code we need is here in the binary search tree.hpp file. It's a template. So everywhere where I see a T, that is of a templated or basically unknown data type. I did the constructor and I